Okay, so back from the break. Let's keep going. So I'm now going to overview some of the other varied pieces of Scala's type system, in part just so you can recognize them syntactically when you see them, but also kind of to understand what they're for to some extent, why they got added. So you've probably seen the with keyword if you've done much Scala coding. It's most common place you'll encounter it is in so-called mix-in composition. And essentially, that's the idea that you can build your software if you sort of follow the inheritance school of development. You build your software in kind of pieces, and you mix together the pieces you want. And this is an example. So the Scala collections use mix-in composition very extensively. And this is actually just lifted. This is the definition of the seq-like trait, which is the implementation of sequences. So this is straight out of the core. And I really just grabbed it because I wanted to show how we take two type parameters here that are actually parameters, and then we're actually composing this trait out of three others: gen seq-like or generic sequence-like, parallelizable, and iterable-like. And we mix them together. But we can also use with in the type level. So with has sort of two meanings. One is when you're defining classes, but secondly, when you're actually defining types. You can use with to create compound types. And a compound type has the types of all of its components. So it's a type that's this and it's that. So here's an example, kind of use case you might want to use it for. So imagine we've got a vector of some type t, and we want the direction of the vector. And typically in sort of maths, you talk about direction vectors always like a unit vector. So it's whatever the vector's direction is, but always has magnitude of 1. So that's going to be a vector too, but we might want to actually tag that in our type system so for type safety we can know, is it a unit vector or is it some other kind of vector? So we can do that with a with type by a marker trait unit length, and say that the direction method returns a vector with unit length. So create that compound type. Let's keep going with that. So type keyword you see quite a bit in Scala, and you can do a bunch of different things with it. One of them is type aliases, and another is type level functions. So let me give you an example of both of those here. This is perhaps a bit awkward, saying vector2 with unit length. We might want to call that a unit vector. And so we can use the type to create a type function. And the reason why, a type function that essentially aliases unit vector of t to vector2 of t with unit length. So now we could rewrite that as returning unit vector t instead, which is a bit more elegant. So why have I called it a type function? Well, it's a type function because at the type level, so in compiler, when the types are being evaluated, we can think of it as saying when it encounters that expression, it passes the parameter t in and evaluates the body of the function, which is what's on this side. And it's kind of analogous to a value level function. This is the name of the function, that's its parameters, and this is the, if you like, the implementation. But it happens at the type level. Alright, so moving on from with and type aliases to abstract type members. So abstract type members allow classes, traits, and objects to define types as abstract members. Like members kind of like means a field or a value. So in Scala, you can have three kinds of things in a class. You can have fields, values, and types. And an abstract member is kind of like a, you know how in an abstract class you might have a template method. It's like a slot that the subclass has to fill in with the appropriate implementation for that subclass. Well, you can do the same thing with a type and say the subclass needs to fill in a type. It's an extension point or slot. Now, I'm not super familiar with these things, so to give an example that's correct, I'm using the one out of Martin Adersky's book. Let's whip up a type hierarchy, different kinds of food. One kind of food is grass, and fish is the other kind of food. So animals eat food, but they don't eat any kind of food. They only eat suitable food. And so for every kind of animal, you have to tell it what kind of food is suitable food. For a cow, the suitable food, that type is grass, and that means that the eat method statically takes a value that must be some type of grass. So we can create a cow, we can tell it to eat some grass, that's fine, but if we tell it to eat some fish, we get a type error. Now, the thing to keep in mind with these type members is that anything you can do with type members, you can also do with parametric polymorphism. If you like, type members is a kind of syntactic sugar or an encoding of generics. But Adersky's argument is that some things can be represented much more elegantly with fewer notation using this abstract type member than you could if you did it with type parameters. Just so you're aware, here's cow written again, but this time we're using a type parameter. So we're saying that the type parameter f, when you create this cow, must be some kind of food. Actually, that should be animal. That should be animal there. Class animal takes some kind of food, eats some kind of suitable food that is of that type that we pass it. So this is just a type parameter as we looked at previously. Okay, so now I'm just going to introduce a thing called the type projection operator. You see, if we're starting to define types in a context, let's say in here we've got a class animal and the type's nested inside it, we just need some way to refer to types that are nested in a context. And so here, that's what this hash does. So it's a little bit like the dot operator in values, except at the type level. So grass has type cow suitable food, and that projects that suitable food type out. Okay, now I'm going to go into something a little bit more advanced now and kind of use it as a case study for trying to understand what we've learned so far. So one place that you might, if you look at, let's say, open source Scala that's been written, encountered the type projection is in a so-called type lambda idiom, which essentially lets you curry or partially apply types instead of values. So what I want to ask is just what we've learned so far tonight enough for us to actually pick apart to decipher this very, very exotic expression we find here in this the return type of functor? And what you'll find is that if we go into this in detail, we've actually learned all of the rules you need to understand this, but we're going to do it step by step. So this is essentially a subset of code from Scala Z, which is a sort of the leading very functional style library outside the core Scala library. I grabbed it because this is a particularly easy, well, the most easy example I could find to show what this type lambda does. But let's understand what it's trying to do and then understand how it got there. So first, for those that aren't familiar, a functor, the idea of a functor is a generalized container. It might be a fixed size container, like it might be a single reference. It might be a container that potentially contains nothing, like option none, or it might contain 0 or 1, like option is a functor, list is a functor, all collections are functors. Basically, some kind of really generalization of the idea of a container. And the word product here in this product method, product basically means like generalization of the word tuple, like some kind of holder of a series of values that's of fixed size. So near enough, what this product method does is if you have some functor f and another functor g, and so you have two containers, it will give you back a container over the pair of them. So a container of that is like basically the pair of f and g. That's a kind of approximate rendering of what this method does. But the thing is that both of them have to contain the same type. Now, here's the trick. The actual content of the functor at now is being left unspecified. It's a parameter we're going to fill in later. It's just a functor of something. So we're operating in general about functors rather than a specific functor, a functor holding strings or ints. And so that's why we have these underscores here. So as a result, if we're going to return a product which is a pair of functors, the final type of this, the final concrete type of this is not known here because the type of the functors itself is still unspecified. So strictly speaking, it's going to be a type function of one argument. It's going to be a pair of functors where the functor type is f and g, but the final content inside them will be provided later. So if an inline function is called a lambda expression, an inline type function is a type lambda expression, just by kind of analogy. And Scala didn't really ever define a dedicated syntax for describing type lambdas. But this syntax above was kind of first, I think, invented or discovered by a guy, Jason Zorg, who is an Aussie. He's from Queensland, I believe. And it's a clever hack. It's this piece of syntax here. And although that might look like something with an alien left on Earth, that's actually parsable with just stuff that we've looked at today. So let's parse this out. As far as I can tell, the round brackets are kind of unnecessary. They're just packaging. You get an error without them, but I don't think they have a meaning. But inside we find this expression that's in curly braces. And anytime you have an expression in curly braces, it is a structural type. So we have this type. It's a structural type. The structural type's a list of members. And we've learnt that one kind of member you have is types. So this is a structural type containing one member. And so the structural type is, the member is called lambda. Scala, like Java, is Unicode-based character set. So people use all kinds of funky non-ASCII characters. We could change that and just type it out as lambda. But this type takes a single parameter a, and on its implementation is a pair, or a tuple, that's the tupling syntax, of functor f of a and g of a. So it's a pair of functors of a for some type parameter a. Finally, the type projection operator just says, well, the type of this whole expression is the type of this piece inside it. So what it lets you create essentially is an inline type function that leaves the final type parameter, the content of this functor, unspecified for you to fill in later. That's why it's a parameter. But everything else, all the sort of outer structure is resolved. Now, just to try and give you a kind of an analogy to think about, I've just written the same thing but now at the value level. So for some class A1, we have two constructors that f that takes an A1 and g that takes an A1. They just construct some value, and the lambda is a function that takes an A1, takes a value of A1 and gives you back a pair of an f of an A and a g of A. That's kind of at the value level what that is doing at the type level. Anyway, that's really like advanced Scala. That's like right at the outer margins of the Scala universe. So I wouldn't worry too much if you didn't feel particularly comfortable with that. I just thought I'd throw that in there, but just see what's out there. Okay, moving along now. Singleton types. So singleton types. So if we just cast our mind back to that original definition, we talked about a definition of types as being classification of values in pieces of your program. So singleton types are when you want to classify a single exact value rather than a class of values. So rather than saying like any number, like int, any whole number or any string, you want to say this particular string. And the way you can introduce them is by taking your value and then putting dot type on the end. So here's a string hello, and now I can say H is the type of the string hello, exactly. That particular string too, not just any hello string, that one. And you can see here that it is more specific than string, because I can't ascribe goodbye to the value H. Okay, so when I first heard of these things, I had a lot of trouble understanding what they were good for. But I'm going to give you an example of what they're good for. And this is like going back to the builder pattern, which maybe hopefully you've seen in the world of Java, where it's pretty widely used. So we have a person builder with some build method that finally does the build. And let's just revise what the builder pattern is. Like, builder pattern lets you kind of it's like a factory that you can give it various parameters and configure it, and then at the end you say, and it's accumulating some state, and maybe it's some defaults for stuff that you haven't provided, and at the end you say build, and it pops out an instance of whatever it builds. So this person builder builds persons, and the only thing you're allowed to configure is their name. We've got a specialized version called programmer builder. Because it's about programming, you can also configure whether or not they like Scala. And you can see down below, we happily set off and we grab a programmer builder, we say, yeah, I like Scala and my name's Ben, so build me, and that works fine. But if we just reorder the statements, it doesn't work. And this is like I'm caught on inheritance here. Programmer builder with name Ben returns a person builder. So we've just slipped from a more specific type to a more general type. And person builder, which is the type of that expression there, no longer has a like Scala method. So you get a type error. We'd have to kind of downcast it. But using singleton types, we can actually say, just as before, but in all of the methods, rather than basing it on like saying I return a person builder or I return a programmer builder, we say I return myself, this dot type. And so now it kind of knows that when I'm a programmer builder, even if I call with name Ben, what I'm actually returning is the this pointer, and it can therefore infer that I'm still this value. We're telling it very strongly that we're threading the builder value through the return value of all the calls. This exact builder, not any old builder. Okay, so I think that's basically it for the various pieces of Scala syntax. Before we finish, I want to kind of go now to a bit more of a conceptual level, and just give you another way of thinking about subtyping and maybe broadening your horizons a bit about how you can encode subtyping without actually having subtyping. So here we've got a classic OO subtyping kind of relationship. We've got a supertype and we've got a subtype that extends it, and it passes some of its data up into the more general supertype. And here you can see something you probably just take for granted. I can create an instance of the subtype and I can ascribe it the type of the supertype. Now, another way of thinking about this is anywhere that I have the subtype, I'm allowed to implicitly convert it to be the value of the supertype. Like super implicitly, like it's just built into subtyping that you can implicitly always rise to your more general types. So you know that Scala also has implicit conversions. So what this lets us do is we can essentially encode that without there being any kind of sub or supertype relationship between these. So let's write the same thing again, supertype and subtype, and notice there's no extend supertype here. I just have to tell it, if I wanted to view subtype as a supertype, how would I go about doing that? And that's what this implicit conversion is about. It's saying, well, for a subtype, create a supertype and thread the A value through to it. And now I can essentially write another line that has a great resemblance to this line, and it's exactly the same. I can ascribe the supertype, but I don't need to have a subtyping relationship there. So we can see that there's parallel there. But some of the most interesting things is kind of what's different between these two designs. And one thing obviously is there's a bit more overhead here. We've got an implicit conversion that we had to define and invoke. It's a bit more complexity. But it's got one really big benefit, and that is that we can choose to view this as a subtype of this in a particular context. Like I can scope this implicit conversion to a region of code, like so, and it's only true around here. So we're saying in this case, like for example, if I'm in a discussion about computers, I can view Apple as a subtype of computer companies. But in a different context, I might not want to view Apple. It might not make sense to view Apple as a type of computer, but rather as a type of fruit. So you kind of your relationships of what is a type of what maybe is dependent on the context you're in. So this has given us a non-global way. Whereas with when we do inheritance, that's a global declaration. It's going to be true for the rest of time and for all of space. It'll always have to be a subtype of that. And the type system is going to have to put in a whole bunch of checks to make sure we never violate that rule. So what this kind of way of thinking does is we can start to think about the type hierarchy is actually, instead of being this big fixed type hierarchy we have to get right up front, it's something that we can actually change its shape and form according to our needs at different times and places. And it was this flexibility that enabled Scala Z to come along and actually extend Scala from outside the core. So when I first discovered Scala Z, I had my OO goggles on, and I kind of thought to myself, hey, they're trying to define all these generalizations like functor that sit above iterable. You know, how can they do that? They need to put that into the core. It doesn't make sense. It's a hack. Because I was still thinking in that very much that inheritance-based, somewhat rigid view. And the more you kind of step out of that, the more the inheritance-based view that you have to get your type hierarchy right up front seems really unnecessarily constraining. So here's an example. We just bring our Scala Z implicit conversions into scope, and now with these in scope, we're essentially the effect that's doing is it's creating new supertype relationships. So we're saying that list, which is a core Scala type, now is a monoid, is a functor. So we can, for example, use the monoid concat operator, or actually it's semi-group concat operator, to concat the results of two lists together, even though list wasn't declared to inherit from monoid. There's another dimension where you can loosen the rigidity of class hierarchies, and that's we're going to revisit the structural types that we introduced at the start of the talk. You see, in a structural type, you're not even declaring that one thing is a subtype of another. You're just saying this type is this interface and this is that interface. So, for example, if I create the structural type sized, I'm saying that anything that has a size method returning int is sized, and I can take Scala collection immutable list that most decidedly doesn't implement any sized trait or type in advance and treat it as sized, because the structural type is just based on what it is, not what it was declared to be a subset of. And finally, notice how here we define something that was just purely a type, so it only existed in the compiler. But you find yourself often doing this in nominal typing with traits. So you'll see things like parallelizable or serializable, or these kind of really lightweight interfaces that are really just, to my mind, trying to describe a type. But you end up having to introduce a class, in other words, a runtime value, when really all you wanted was a type. So structural typing is a bit more lightweight in that way. So thanks for your attention. It's been a bit of a long journey and a lot of complex stuff. I hope you learned something from it, and yeah, I'll do part 2 in a few months' time, which is on designing with static typing. How can you use static typing well to get the maximum, wring the maximum number of bugs out of your code, and write really correct code from the outset. Thank you.
Cool, thank you.